Today I'm going to be looking at something completely different, which is debouncing your switches. This is the basic circuit that I'll be starting with, and this is the oscilloscope reading with just the resistor alone, and you can see the mess that we have. Look at this spike that lasts almost 25 microseconds. Next I'm going to add a 10 microfarad capacitor as outlined over here, and you can see that the fall time of the pulse is quite long. It takes 216 milliseconds to fall, and the rise time is similarly quite prolonged as well. This is not the official way you're supposed to calculate the rise and fall times, but I think that if we can switch across 4 volts, we will have a pretty reliable signal. Adding a diode across R3 shortens the rise time, but it's still pretty long. So the next experiment is with a 1 microfarad capacitor. This shortens the fall time, but the rise time still stays long because the capacitor is being charged across 2 resistors. If we add a diode across the second resistor, the rise time then shortens to almost the same as the fall time. Feel free to look at the diagrams. Pause the video, please. Now here's what the diode looks like when it's across the second resistor, and this time we're going to use a 0.1 microfarad capacitor. And we'll check without and with the diode for the rising edge. Falling edge is quite brisk, 1.6 milliseconds, and the rising edge is similarly nice and short. And I will show what the diode looks like in a later picture. It's just a cheap old 1N4148, nothing special. Ideally one wants to use a Schottky diode for that location because it'll have a shorter rise time and also a smaller voltage drop across the diode. Next we're going to use a 1K value for the second resistor. This is the resistor that limits the discharge current from the capacitor, basically keeps it from shorting out and creating a huge current spike. The rise time is 1.84 milliseconds. The fall time though is much faster because the capacitor is now discharging across a 1K resistor rather than a 10K resistor, and you will see that in just a moment. The fall time is only 160 microseconds, which may be a bit too fast for our needs. Next I'm going to be mashing on the button a bunch of times and look at what the waveform looks like. This is 50 millisecond time base, so each big box represents 50 milliseconds. And as we zoom in, you can see that the edge looks very sharp and clear. It's only when you get down to about the 2.5 millisecond time base that you start to see a little curve. And 100 microseconds, you can certainly make out the discharge curve of the capacitor very nicely. And now you'll see an interesting little jagginess to the waveform, and even though it's jaggy here, the span is only 1 volt, and I don't think it'll accidentally trigger anything. And again now with lots of rapid clicks. Time base is 100 milliseconds, and you can see that the waveform is very nice and crisp, and no doubt that there's a high and a low. And then next I'm going to show the waveforms with my preferred setup, which is 0.1 microfarad capacitor and 2 10K resistors. Again, at 100 millisecond time base, perfectly fine. Feel free to pause the video at this point and take a look at my different combinations. They show what the rise and fall time is, and I think a 17 to 20 odd millisecond rise and fall time for the edge is perfectly acceptable if all you want to do is to see what your button push does and read it into a microcontroller. The next item is to add a Schmitt trigger to the output coming from the diode, resistor, and capacitor combination. This basically just sharpens everything up. It gives an even cleaner edge because when you were looking at the zoomed in waveforms, you could see that there was a slope at the rising and falling edge from the capacitors, and this will smarten that up, Schmitt trigger basically has a zone of hysteresis, and it will trigger and it won't re-trigger until it falls below and then rises above the hysteresis zone. This shows the setup on my breadboard, and again, feel free to pause the video here to take a look if you like. The chip is cheap, very easy to use, pretty sturdy, and so it's a case of why not. You can see the Schmitt trigger output in blue, and even though there is a very nice curve on the yellow, which is the output from the capacitor, the blue output showing the Schmitt trigger output is crisp and basically a straight fall. So if you are trying to read something into a microcontroller and you want to make sure that everything is going to be exactly right on the money, well, a Schmitt trigger is cheap and sure. Well, I hope this video was useful, and if so, please do like and subscribe. Thanks for watching.